So today the goal is to cover the following topics: AWGN model, bit error rate, what is meant by SNR, what is meant by EB by N0, and look at one basic simulation. I will tell you how to do a basic simulation on MATLAB. And then and I will start with the single tap model, and if time permits, I will talk about pilots. Okay. So this is what we are going to cover today. So let's just recall what we have done in the last class. In the last class, we have looked at the transmitter and the receiver, block diagram. And in the block diagram, what we have understood was we could capture everything by this model, y is equal to x plus noise, z. Okay, where x is the modulator, x is the constellation point you send, and z is the Gaussian noise. Z is the complex Gaussian noise. Okay, so this is what we learned last class. Okay, so this is called additive white Gaussian noise. So since we are in the discrete domain, I'm going to write this as y of n is equal to x of n plus z of n to explicitly indicate the time. So this n is nothing but the time, discrete time. Okay, so 1 second, depending upon, so essentially n is the number which says, okay, this is the first time instant you are using the channel, second time instant you are using the channel, third time instant, so on and so forth. Okay, so this is called the discrete model. This is what we will mostly work with. Okay, okay, recall x of n was the constellation point, z of n was the additive white Gaussian noise. Okay, I'll tell you what is meant by white. Okay, I mean Gaussian noise, you understand. Gaussian noise essence is a complex Gaussian noise, so essence is z of n is equal to z in phase of n plus I times zq of n. Okay, so essentially this is what we have. Okay, good. So let's dig it a little bit. So essentially, what are the other things that we have learned? We have learned that the power in the noise is expected value of mod z of n whole square is the mean value of the power. Okay, the mean value of the power is equal to sigma square. Okay, out of the sigma square, what we have is half of this is in the imaginary part and half of this is in the real part. Expected value of mod zi of n whole square is equal to sigma square by 2. This is also equal to expected value of mod zq whole square. Okay, so both of them are equal. Real parts and imaginary part powers are equal, and the total is equal to sigma.
So what is E over here?
E is called expectation. So okay, what is meant by expectation? Okay, I'll just give just a brief thing. Suppose you have a random variable x. Essentially, x is a random variable. Okay, so essentially x can take any value. For a Gaussian random variable, x can take any value between plus and minus infinity with this probability density. Okay. So what is expected value of x? Expected value of any function of x is nothing but essentially what you do is you generate this random variable multiple times. Okay, so you generate the random variable multiple times and you do x1 plus x2 up to xn and you divide by n. Okay, this is what expected. So what is meant by expected value of x square? It is x1 square plus x2 square all the way up to xn square by n. As n becomes larger and larger, both of them become equal. Otherwise, it's a small approximation is there, but as n becomes larger, these become close to each other. This is what essentially it's the mean of whatever is there inside this. Okay, so for example, for a Gaussian random variable 0 mean, what is expected value of x? This will be 0. Okay, So if you have n01, that is Gaussian random variable mean 0 and variance 1, this will become 1. Okay. So in general, expected value of f of x, where f is some function of the random variable, is nothing but the way to think about this is you take this function, evaluate it over multiple realizations of that random variable, and take the average. Okay, and these become very close to each other as n becomes larger and larger. That's how you should interpret them. Okay, so in this particular case, so every time z has different value, no? Because it's a random variable, it's Gaussian. Okay, so what I'm going to do is I'm going to take the mean value of the squares of the power. Essentially, the squares represent the power. Okay, I'm going to take the mean value of that. The mean value of that will be equal to sigma square. Is this clear, sir?
Now it is clear, sir.
This is called expectation operator. Okay. Good. So next, okay. So so this is what we have, and we also did one more thing. We also had signal power. Signal power. Essentially, we use a normalized constellation. So since we use a normalized constellation, this was always equal to 1. This is what we did last class. Agreed? Okay. So let me just write the model again. So that we always have this. Y of n is equal to x of n plus z of n. Okay. So I'm going to define my signal to noise ratio. Signal to noise ratio, it's also called SNR. Okay. Okay. Is defined as signal power by noise power. Okay. So what is the signal power in our case? What is it? So in this thing, the signal is this. This is a noise. Okay. So this is a signal. So what is the power in the signal? What is the power in the signal?
X square.
Yeah. Essentially, you should take expected value of xn square. Okay. So this is the signal power. This is equivalent to 1.
1.
Okay. And what is the noise power? Expected value of Zn square, which was equal to sigma
square.
Yeah. So our SNR is equal to sigma square. Okay. So this is also sometimes is also denoted by as ES by N0. Okay. So in general, what you can think about is N0 and sigma square are related. N0, I mean, most of the times you can think of this as N0 is equal to sigma square. I mean, there's a time scaling factor which we don't generally put, but this is there's some interpretation for this. You can think of this N0 is nothing but the power spectral density, and that's equal to sigma square, because some time gets cancelled in both ES. So this is energy, this is not power. Similarly, this is spectral density. So the time gets cancelled and becomes power. So N0, you can think of them as sigma square. This is also represented as ES by N0. ES is the symbol energy in the symbol X by energy in the noise. So ES by N0. This is also called as SNR. Both of them are the same. Okay. So did you understand how, essentially someone gives you a model like this, you should be able to identify what is the signal component, what is the noise component, and be able to find out the signal to noise ratio. Okay, this is good. Any questions before I just move? Okay, good. So there's something called EB by N0. Okay. So EB by N0. So this is nothing but SNR for the symbols. Okay, for the constellation point. X of n is a constellation point. Okay, remember that. So SNR is for the symbol. This SNR is for the symbol. But EB by N0 is for the bits. You can think of EB by N0 is equivalent to SNR per bit. Okay. So what does this mean? Let's take BPSK. Okay. So in BPSK, each bit, one bit is mapped to what? One bit is mapped to one symbol. Yes, now. So essentially we had minus 1 and this is plus 1. So 0 was mapped to here, bit 0 was mapped to here, bit map 1 is mapped to here. Okay, so one bit is mapped to one symbol. Okay, so the energy per effective energy per bit is equivalent to effective energy per symbol. Okay, so what we have for BPSK is SNR per bit is equal to SNR per symbol. This also implies that EB by N0 is equal to ES by N0 is equal to SNR for BPSK. Okay. Is this clear? Let's do for QPSK, it becomes clear. In QPSK, one symbol, how many bits are there?
2.
2 bits. Okay. So SNR by SNR per bit will be equal to half of SNR per symbol. Okay. So it implies EB by N0 will be equal to half times ES by N0. Agreed? Because each symbol has 2 bits. Okay, if you divide the power between the 2 bits equally, which is the case, I mean, these 2 bits will have half the power and therefore half the SNR. Okay, so in general for MQAM, what we have is, we have EB by N0 will be equal to 1 by log 2 of M ES by N0. Okay, or SNR per bit is equal to 1 by log 2 of the modulation order into SNR per symbol. Is that clear? So if you have 16 QAM, 4 bits are representing each symbol. So the energy per bit will be 1/4 of the energy per symbol. Okay. Any question? The reason I'm introducing EB by N0 and other things will become clear. See, essentially, when we compare two different modulations, it's better to use EB by N0 rather than SNR in general. Okay, it will become clear in a minute. Okay. So now, this is what is meant by definition of an SNR. Okay. So now let's look at let's just understand what are the metrics of interest. Okay, so you have bit, BI is bit is bits are mapped to constellation points, and this is what I call as SI, the constellation points, and then you are adding noise to this. Effectively, noise is getting added, and once we get the constellation point, we are mapping it into something. And this is what is called this mapped, so you're estimating what is the transmitted symbol. From this, you are estimating, you are decoding the bits. Decoding bits, and these bits are called BI hat. Okay, so you transmitted BI, and the receiver, somehow you felt that BI hat was transmitted. Okay, so what is meant by bit error rate? Bit error rate is the probability is I denote like this, that BI is not equal to BI hat. Yes, that is intuitive. No? Essentially, you transmitted BI. Somehow you did some receiver processing. This part is the whole receiver. You did some receiver processing, and you think and you declared that BI hat was transmitted. Okay, so bit error rate is the probability that BI is not equal to BI hat. So what does probability mean? It means that you count the number of times there's an error and divide by and average it out. Okay? That will give you the probability. Similarly, you can define symbol error rate. Symbol error rate is the probability that SI is not equal to SI hat. Of course, both of them are related. It's obvious that if the symbol error rate is high, bit error rate will be high, and vice versa. They are related in that manner. For some constellations, very easy mathematical relation between bit error rate and SCR. For example, BPSK, what happens? Bit error rate is equal to symbol error rate. It's obvious because one bit is mapped to one symbol. Is this fine? Any questions? Okay. Okay. So for AWGN channel, we can find theoretical results for symbol error rate and bit error rate for MQAM. Okay, at least bit symbol error rate we can find the theoretical results, and bit error rate some small approximations will be there. Okay, so these are generally in general expressed in terms of Q functions. Okay, I'm going to show you some examples. Okay, I'll just show you an example of how this looks like. Okay, so for example, the probability of I think this is the symbol error. This is the probability of symbol error is given by this expression for an MQAM. That's not actually true. It's not half. It's something a little bit different. Okay, Navya, that's not exactly half. Symbol error rate is not, bit error rate is not half of symbol error rate. Okay, it's a complicated expression. Okay, it's a complicated expression for probability of error. Okay, it is denoted in terms of Q function. Q functions are nothing but exponential integrals of exponential functions. Anyway, let's not bother about this. Okay. So we will have a better way of doing this using simulations. I will explain you that in a little minute. But what I want to emphasize is there are theoretical expressions for the bit error rate of MQAM. MQAM, MPSK is, I mean, even for PSK, I mean, MPSK is also there. Expressions are there, MQAMs are there. Some specific constellations, there are lots of nice theoretical expressions for the bit error rate and the symbol error rate. Okay. But what I want to do is, I want to understand how do we generate this using simulations. Okay? Because that's what, see, when for simple things like MPSK, MQAM and other things, you can draw theoretical constellations. But when things become complicated, you cannot have this kind of theoretical expressions. Okay? Rather you should be, you will be relying on simulations to do this. Okay, so how do we simulate and find bit error rate of a particular modulation? Okay, so this is what I'm going to show you in a little bit. Okay, I'm going to take 5 minutes and show this. Okay, so to do this, I'm going to use MATLAB. I don't know how many of you are aware of how to use MATLAB. Okay, for now it's a pretty simple programming language. I'm going to show you how to use MATLAB. MATLAB for now. I've also provided links for all of you to install install a MATLAB license. Please go ahead and do that. From next week onwards, I'm going to give assignments in MATLAB. Okay, for example, to generate the bit error rate curves of QPSKs and other things. Okay, we require this. Okay, so for now, what I'm going to do is, so first let's write up the algorithm. Let's write up the algorithm on how to generate this, and then what we'll do is I'll show you the MATLAB code. Okay, so this is simulation methodology. So you remember, always you remember your model. Y of n is equal to x of n plus Gaussian noise, and the power in the noise is sigma square, and your constellation is unit energy. Okay. Please feel free to stop me at any point. Okay. So the question is, how do we find BPSK? I'm going to show you the example of BPSK, but you can do the same thing for other modulations. Okay. So you start. The first step is you generate one bit, call it BI, randomly. Remember, our bits are uniformly random. So each BI we should take one with probability half and 0 with probability half. Okay. The second step is map BI to a constellation point. Okay. And the constellation point is what we call as X of n. The third step is add noise, add Gaussian noise. Okay, so we have y of n is equal to x of n plus z of n. Essentially, generate z of n and add that. Okay. The fourth step is the receiver step. Decode the Rx, the symbol x of n. And the fifth step is map the Rx symbol x hat of n to bits. Okay. Sixth step is see if there is an error. What does it mean? So essentially error is equal to 1 if bi hat is not equal to bi. Okay. Seventh is go back to start. Okay. So you go on doing this. Okay. So did you understand the steps? Essentially, this is exactly what whenever I do a simulation, I always follow what happens in a transmitter, what happens in a channel, and what happens in the receiver. Okay. So what is your transmitter here? This is these two steps are your transmitter. First two steps are your transmitter. The third step is your channel. Essentially, channel is something that's a wire or something. Okay. And fourth and fifth steps are what? The receiver part. Okay. So whenever I do a simulation, I always have a transmitter, a channel, and a receiver. Okay. So I mean,
Professor, this is VK Roy. Actually, this channel is LTI, na? This channel AWGN channel is the LTI.
It's a linear time. Yeah, but it's just a simple Gaussian channel. There's no channel. I mean, there's no filter or anything. I'll come to that later. This is simple, very simple additive Gaussian noise channel. Okay. Okay. So
but it is linear and time invariant, no?
It's also linear and time invariant. Yeah, that's all. Sir. This is not time invariant. This is not LTI system. Okay, because the noise changes over time. Okay. So LTI systems are generally filters.
Okay.
Okay, so this is not an LTI system.
What can be told about this channel?
So this is just a Gaussian channel. Okay, so essentially it's called additive noise. Okay, so essentially you're taking x of n.
Noise is coming from somewhere.
So if you please okay. So yeah, Shahim is asking if how many times you have put in the loop. I'll tell you that. Okay, so let's see my MATLAB code. I hope you can see my screen. So this is MATLAB has this is called the the console, and this is the editor. Okay, so I'm going to show you the 6 steps. I'm going to tell you how to use this for just QPSK. I'm going to do this example. Okay, first I'm going to generate the bits. Okay, so I can use something called random integer. Essentially generates an integer between randi a generates a random integer between 1 and a. So randi 2 will generate an integer between 1 and 2. So randomly it will generate with equal probability 1 and 2. If I subtract 1 minus 1 from that, b will always be 0 and 1s. Okay. So if you want to see any help in MATLAB, you should put doc the function name. Okay, it will tell you. Okay, random. Next, I'm mapping to the constellation. I'm saying that if my bit is 0, I map to 1. If my bit is not 0, I'll map it to -1. Okay, so this is my transmitter is done. Okay, and then now I generate Gaussian channel. Okay, so x of n is real here. Okay, so I can only worry about the real part. because there's no imaginary part for BPSK. And for QPSK, you might have to put the imaginary part also. So what I'm going to do, I'm going to generate a Gaussian random variable with unit mean and unit variance. Okay, so I'm going to tell you one property of Gaussian random variable that is useful. Okay, so that simulations become easy. So one property of Gaussian random variable is if X is a Gaussian random variable, this is how I denote now. Gaussian random variable is zero mean and unit variance. The unit variance means expected value of x square is equal to 1. Okay. Suppose I want to generate one more random variable. Suppose, so this is a Gaussian random variable that's given to you. Suppose I want to generate y, which is Gaussian, but variance sigma square. Then how do I generate this using x? Okay, all I have to do is, if I set my y is equal to sigma times x, I just multiply sigma with x with sigma. Okay, then y is Gaussian with mean 0. Again, the mean won't change, and variance sigma square. It's very simple. Okay, so see that expected value of y square will be equal to expected value of sigma x whole square, which is equal to sigma square into expected value of x square, which is equal to sigma square, because expected value of x square is 1. Okay, so we'll use this property. This is true for in Gaussian, you can do this. Okay, the mean won't change. If you want to have a mean, you have to add that mean here. Okay, if you want a mean. But anyway, let's not worry about that right now. Okay, so based on this, I'm going to do this simulation. So I'm generating random generates a Gaussian random variable with 0 mean and unit variance. Okay, it generates 1 comma 1 means it generates one random variable. Otherwise, you can generate a vector of random variables also. Then I'm multiplying with the noise variance by 2, because each dimension from real part and imaginary part will have noise variance by 2. I'm taking the square root of that. Okay, remember sigma square I multiply by sigma. Then I'm adding it to my x. Y is equal to x plus noise. Okay, so this is where my channel is done. Now my channel is done at this point. Now I'm coming to the receiver. How do I decode my BPSK? BPSK is very simple. Okay, I got my y. When do you declare 1 was transmitted and when you declare -1 was transmitted? Can anyone tell me?
Sir, midway, if it is above midway 1, below midway -1.
Exactly. Okay, so this is called nearest neighbor decoding. Essentially, in BPSK, you have 2 points, and you are going to receive some point somewhere. Okay, so if you receive the point here, what you do is you map that point to here. On the other hand, if you receive the point as here, then you map it to other way. So you map it to the nearest constellation point. Is it clear? This is called nearest neighbor decoding. Nearest neighbor decoding. It turns out this is optimal decoding when there is additive white Gaussian noise channel. Okay, I mean, I'm just going to state that fact. I'm not going to tell you why it's proved that way. Okay, so here what I'm doing, I'm checking if y is greater than 0. That means 1 was transmitted. One symbol 1 was transmitted. Symbol 1 implies my bit is 0. On the other hand, if y is negative, whatever you receive is negative, -1 was transmitted. -1 implies my bit was +1. Bit 1 was transmitted. Okay, so this is where my decoding happens. Then I check if there's a bit error. How do I check my bit error? Since it's a simulation, I know what is transmitted. This is what I transmitted. I'm checking with if that is not equal to what I received. I make error 1. Okay, so this is a basic 6 steps. Then what I do is, so if I run this once, I am just going to write error is equal to 1 or 0. Hello, any question please? So then what I do is I run this multiple number of times. So for example, here I'm running 500,000 times. The same thing. I'm generating random bits every time, adding different kind of noise and checking my error. Okay. And I also run it across all the SNRs. Okay, you can check this. So how many times you have to run, I'll show. Let me run this once and you'll see how the curve is generated. Okay. I'm going to make it a little bit bigger. You see my this thing now? Okay, you see this curve now? Okay. So on the x-axis, what I plotted was, so this is called a semi-log Y plot. Okay, in the x-axis, EB by N naught is there in dB in terms of dB scale. On the y-axis is the bit error rate. So what this says is at 6 dB SNR, the BPSK, you get approximately 0.002 bit error rate. Okay. At 10 dB, you get approximately 10 power minus 6. Okay. So this is called the bit error rate curve. It's called a waterfall curve. You see, it's falling like a waterfall. Okay. So this is one of the most important metrics in digital communication system. Finally, this tells you if your communication is reliable. Yeah, here I have not added any LDPC code or anything. This is just plain vanilla constellation transmission over an AWG channel, receiving it, decoding it, finding the bit error rate. Is this fine?
Sir, did you get this curve from simulation or from the formula?
Simulation. I just ran my MATLAB code. I just put a run. Okay. So what I did was, then what I do is I also do a loop over the different SNR values, change the noise variance based on the SNR, and run this loop. That's what I do. I'll share this program. It will help you understand how to do the bit error rate curves. Okay. You can try out for QPSK, 16 QAM and other things. Fine. So this bit error rate curves are finally the most important metric. Other than, of course, the spectral efficiency and other things, this is the most important metric for determining the performance of your system. Okay. So I'm going to show you. Sorry. I'm going to show you some more curves. Just 1 minute. So this is something that I found on the net. So this is the bit error rate curves for 4 QAM, 16 QAM, 64, and 250. See, they're putting it in terms of EB by N naught, not SNR. Okay, because SNR for symbol differs for each of these modulation schemes. So if you want to compare schemes, it's always better to use EB by N naught because it's always energy per bit. Okay. So if you see this, one thing that you're going to observe is between these two curves, approximately there's going to be 6 dB space. So effectively it turns out every bit you add for the same bit error rate that you want. Suppose I want to fix my bit error rate at 10 power minus 4. But or better, I mean, generally this is told at 10 power minus 6. At 10 power minus 6, then every bit increase requires you to increase the EB by N naught by 3 dB to maintain the same bit error rate performance. Okay. If you go to 4 QAM to 16 QAM, approximately the 4 QAM to 64 QAM has 2 bits per symbol and 16 QAM has 4 bits per symbol. Okay. So you're doing 2 bits. You can see approximately the gap is 6 dB. And when it goes a little bit lower, the gap becomes exactly 6 dB. Okay. So essentially per bit to maintain the same bit error rate, approximately it takes 3 dB. 3 dB difference. This is a thumb rule. Okay. And BPSK and QPSK 4 QAM will have the same bit error rate. In terms of EB by N naught. Any questions before we proceed?
What is physical significance of this? If we add 1 bit, so we'll have to increase the signal of if
EB
we
by N
go from okay.
So, sir, essentially look at this. Sir. Look at this curve. Suppose you can see my cursor. It's a little bit dull, but you can see my cursor now. It's
Yes,
a 10
yes.
power minus 4. Suppose I want to
Okay.
maintain my probability of error at 10 power minus 4. Bit
Right.
error rate. Okay.
Right.
You see, 4 QAM requires approximately about 7 dB EB by N0.
Right.
4
Right.
QAM is a blue curve.
Mm-hmm.
On the other, the 16 QAM requires about 13 dB, approximately 13 dB.
Right.
For maintaining same 10 power minus 4. The gap is approximately 6 dB. Okay.
If we
So-
go for SNR, I think there is relation between bit error rate in AWGN channel and SNR also. And
Yes.
there is relation between SNR and EB by N0.
Hmm.
So can you show this graph for SNR also?
I don't have it with me, but what we'll do is we will generate those curves as homework problems.
Right.
Okay, I can share those with you also. But in general, they don't compare SNRs mainly because SNR differs per constellation. I mean, the x-axis is different for all of them. It does not make sense to have a common x-axis. Yes,
But
EB
in error, what is the I think EB by in not we understand, but in physical error in 4G and all, what which term is more important for us, whether it is SNR or EB by N not only?
There are some places where we use SNR. There are some places, for example, when we do the error curves, finally EB by N0 matters. Okay, because
right.
On top of this, what happens is you also add FEC. When you do FEC, the relation between SNR and EB by N0 is a little bit more complicated because you have also added redundancy. Okay, I will explain you that when we do some simulations. I'll explain you that, sir, as we progress. But I think for bit error rate, let's stick to EB by N0, and for something else, we can stick to SNR. I mean, at that point, it will become clear for us.
Okay.
Sir,
but the thumb rule is who is
sir, I
please,
think
sir,
this
please.
graph represents the trade-off between symbol energy and bandwidth requirement. Is it so?
Symbol energy and bandwidth requirement. No, actually, there's no
trade-off. Because when
There's
we are clubbing the bits to reduce the required channel bandwidth, in a sense.
It's a very I mean, in a very implicit manner, it represents that. That's true.
Okay. Okay.
In a very implicit manner, it represents it. So, for example, when you send 16 QAM for the same bandwidth, you're pumping in more bits.
Yes, sir.
Okay, for the same bandwidth.
I mean, to pump more bits, we can use less bandwidth. It can be said the reverse also.
Yes, the other way also can be thought. But
yes,
to say that for the same bandwidth, you're pumping in more bits, but the penalty you pay is in terms of the power that you have to require to transmit.
Okay. Yes,
okay, because
that's the trade-off.
To maintain the same bit error rate, you require more power.
That's why this 6 dB increase between these two curves.
Yeah, between these two curves. Yeah. The thumb rule, easy to remember thumb rule is each bit is 3 dB.
Okay, sir.
Each bit is 3 dB in terms of EB by.
Okay. Sir, I just want to say that this is what the Shannon also said that C is equal to B log 1 plus log 2s by n. That if you increase the number of the bits, that you cannot go on unless you have to see about the signal to noise ratio also.
Yes, sir.
In the same case, EB by NO, with the same bandwidth, we have to increase the power to get the required BR.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. This also, all of them are related in some implicit manners. I mean, it's there in the textbook. There, I put one textbook where you can actually read up the relations between all of these things. I will add that book to the Google Classroom today. I mean, I'm not going through all those things in detail because, it will take us out of, I mean, that itself will take a long time for us. Okay. So, this is good. So, what? Please.
Sir, how did you get to know the 500,000 figure for number of repetitions?
Let me tell you that, explain you that. Okay. So the thumb rule is very simple. There's a thumb rule. Okay. It's not a mathematical rule. There's some mathematical relation to that. So if you want an SNR bit error rate of 10 power minus 3, you have to simulate for 10 power 5 times. 100 times inverse of the bit error rate. So you should roughly have an idea of how much your bit error rate is. and you have to do 100 times 1 by 100 times inverse of that error rate, so that things converge. That's all. There's no easy way of putting this for 500,000. I don't have to do 500,000 for the initial EV by naughts. Only when I go to 10 dB, where I require 10 power minus 5 and all that, to get a smooth curve, I have to do that. Okay. At some stage, tell me.
Sir, in optical communication, the bit error rate will be some 10 power minus 12. So, is it feasible to run it 10 power 12 times or 14 times?
There are other techniques to do that, something called importance sampling and other things. Okay. I think let's not, you have to use some MCMC, Monte Carlo analysis ways of doing that, importance sampling and other things. But you can contact me offline. I'll tell you that. I don't want to do that in this class. Okay, the simplest way, thumb rule is, if you can simulate, if you have enough computation power, just go ahead and simulate so many times. Okay?
Okay, sir. So we have to know how much approximately it will be.
Approximately. Generally, make sure your curve is smooth. That's good enough.
Okay, sir. Thank you.
Okay. Good. So the first assignment I'm going to give us, simulate BER curves, BER versus EV by N0 for QPSK, that is 4 QAM. I mean, let's do 4 QAM now, QPSK. 4 QAM, 16 QAM, and 64 QAM. Okay? Sorry. Okay, so this is what I want you to simulate. This is your first MATLAB assignment. Okay, this will also help you to understand how to write a program in MATLAB. The TS, I can ask the TS for the people who do not know MATLAB. I'll ask the TS to take one small tutorial on doing some basics of MATLAB. Okay, one small tutorial on basics of MATLAB.
Yes, this is needed, sir. The tutorial on the basic of the MATLAB.
I'll ask them. So we'll take. So for this first assignment alone, I'll give about 2 weeks. You can even submit a bit late, because I want all of you to engage in MATLAB and make sure that you understand how to do this. Okay, we'll take some time and do this slowly. Fine. So I will coordinate with the TS and.
So can we have a separate walkthrough for the MATLAB thing?
Yes, we'll have a separate walkthrough. I am myself or the TS, one of them will do this. Okay. We will have a separate walkthrough one day, one special class, or sometime we can set it up and do this. So the next channel I'm going to introduce is a little bit. Okay. Y of n is equal to A times X of n plus Z of n. Okay, before we go this, there's one small thing I have to tell you. Why is it called AWGN channel? Gaussian part is very clear. Okay, Gaussian means essentially they are drawn from Gaussian. All of you know that. Additive part is also very clear because you add the noise. What is this white part of the additive white Gaussian noise? What white means is, so we are writing Z of n. Every time you're generating a Gaussian random variable, it turns out in additive white Gaussian noise, Z of n and Z of n plus 1 or any other Z of k are independent of each other. Okay? They do not have any relation. So by looking at Z of n, you cannot tell anything about Zn plus 1 or the future noise. The noise is independent across time. That is called white. Okay. So in the spectrum analyzer, what does white mean? White means if you look at the noise, the power spectral density of Gaussian noise, it is flat in the frequency domain.
Sir, here also I want to add that white is also called because its noise is there at all the frequencies.
Yes. The reason why it has all the frequencies is it's uncorrelated. Essentially, you do something called as autocovariance. Okay. It turns out the autocovariance is a delta function, which implies that in the frequency domain, it has all the frequencies. Okay. So the interpretation of this white in terms of time domain is not in the spectral domain, but in the time domain is that the noise at this time has no correlation with the noise before or after. Essentially, you cannot tell anything by looking at the noise now. You cannot tell anything about the noise in the future or in the past. Okay, that is called white. There is something called colored noise also. The colored noise channels also happen when you do some things. Okay, but we will always focus on AWGN channel. Most of the work is on AWGN channels. I just wanted you to know that. Okay. So the next channel is it looks very simple, but it has a lot of implications. All I did was I multiplied by A is a complex number. Okay, it's the same thing except that now you have a gain or loss, whatever. I mean, I generally call it gain. Gain also means that it can be less than 1 in my interpretation. Okay. So why does this happen? For example, you are transmitting a signal on the air. Let's assume no multipath or anything, simple, plain. Let's assume you are in vacuum, just for simplicity. You are transmitting and your receiver is far away. Okay, then what happens? The signal power decays. Yes, the signal power decays, and once you hit the receiver, noise gets added. So this models, in some sense, models the gain or the loss that you see in the medium. Still, it's a one number only I'm putting. I'm just multiplying by a single number. A into X of n plus Z of n. Fine?
So yeah, what do you mean by the next channel?
Huh? I mean,
I'm saying the next channel.
No. I'm just saying, I just wrote it as next channel we are looking at. So this is also AWGN channel with a gain factor. Gain factor. Okay, this is one way of interpreting it. Other way of interpreting it is this is called a single tap channel. Okay, there's only one tap. I will understand why it's called a single tap channel later. So this A is a complex number. Okay. So when you have something like this, how do we decode? Okay, how do we decode? So let's start with the assumption. Suppose let's start with the case where case
1. Excuse me, sir.
Ms. Simon, please tell me.
So this A is a constant or a random variable?
That's what I'm coming there.
Okay.
It's a very good question. First, let's assume it's a constant for now. Okay, we'll come to the random part later. Let's even assume the case. Suppose you know A at the receiver. Somehow you know the A at the receiver. Let's not worry about how you know. Okay, let's assume you know the A at the receiver. Okay, let us first understand how do you decode this. Okay, let's take for example simple channel. Let's take an example. Y of n is equal to 0.5 times X of n plus Z of n. Suppose we have this. Okay, I'll just take 5 more minutes and then we'll conclude. Y of n is equal to 0.5 into X of n plus Z of n. Okay, let's say, then what do we think that we should do at the receiver? So as to use our old receiver, older. So we have a chain, nice chain. So I want to use the same old receiver chain. Okay, so what should I do? What do you think we should do?
We may divide by that value at the receiver.
Yes. You see, essentially what, I don't know who told this, but what he was telling is you divide by 0.5. You call this as some y tilde hat is equal to X of n plus Z of n by 0.5. Okay. So this is called zero force. This is a very simple case of zero force. Essentially, when you divide directly by the channel, when you invert the channel, this is called zero force. Okay. So what is the SNR in this case? Let's look at the SNR. Can someone, let's look at the SNR. What is the signal power that we received? After you divide, let's assume that you divided, or even before also, you can do it at any so sorry, yeah. So what is the SNR that we have? So if we just look at the second equation, if you think of this is our equation, what is signal power? Signal power is still expected value of x. This is the received signal. This is the signal that we want. Na? So that's expected value of x and square. That is 1. Noise power is different. Noise power is, no, this is your entire noise is this whole thing. Yes? Expected value of z of n square by 0.5 square. Okay, there's something fishy here. Okay, we'll come back to this. I think yeah, I have to tell you one thing more before I go here. Okay, so we'll stop at this point.
Sir, SNR will go up by 4 times, sir.
No, it can't go up. Of course, SNR can't go up. So there's some small thing that I have to tell you before we get into this. That's what. Yeah, I didn't realize that I have to tell you that before. Okay, so we'll stop at this point. And in the next class, what we'll do is we'll understand, as someone was asking, what happens if A is random? Okay. And the second case 2 is, suppose you don't know A at the receiver, what do you do? Okay, we'll answer these 2 questions. Okay, and we'll also plot the SNR bit error rate curve for 0 forcing. I'll tell you what happens. Fine. Sounds good. Okay. Thanks everyone. Sorry for the confusion today. We always use the same link. I will update the Google Calendar. My apologies for the same. And we'll meet up again on, when is the next class? I forgot. In the next Tuesday. Yeah. Okay. Thanks everyone.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.